This is the Midterm Lit review for suture applications for the Tissue Engineering CI. Just an overview of this whole project, we're basically showing that electrospun nanofibers show great potential for drug delivery. This is due to their high porosity, their high surface area to volume ratio, and their electrostatic charge that allows various drugs and proteins to attach and electrostatically bind to the surface. There is a promise for electrospun nanofibers as sutures due to the fact that there's a large range of polymers compatible with electrospinning, and these polymers can also be biodegradable. We are also able to determine the size and the diameter of the fibers by adjusting the parameters of the electrospinning process. The Lit review looks over 5 journal articles, including surgical site infections, local anesthesia, braided sutures, antimicrobial sutures, and sutures for ocular surgery. In our surgical site infections, we have developed a twisting method for the generation of nanofiber-based sutures, which are capable of simultaneous delivery of silver and gentamicin. Silver and gentamicin both help prevent these surgical site infections. They found that their suture diameters ranged from 80 micrometers to 1.2 millimeters, and that the initial bursts of gentamicin and silver had a sustained release over 5 weeks. This image shows that basically you can twist the fiber and that you can see the difference between the cross-section of their coaxial nanofiber with silver and gentamicin compared to their simple PCL, which is polycaprolactone nanofiber. The next one for local anesthesia used a PLGA fiber. They found that the tensile strength decreased as their drug content increased, and that local anesthesia was achieved 1 day after surgery and lasted approximately a week in 90% of their treated animals. All wounds were able to heal without the need for further reinforcement, so they were able to obtain that tensile strength, and they found that their goal is to decrease or eliminate the need for that post-operative opioid medication. And you can see in this image that their suture is actually not twisted like ours is. It's a little bit more straight and not as there's not as big of a twist per inch ratio. As for the braided sutures, this is a PLLA nanofiber, which is collected uniaxially. It was made into a more compact braided wire. In this, the nanofibers were collected by a high-speed rotating disc, which displayed this uniaxial orientation. They then used a custom-made device, which combined hot stretching and twisting for 2 hours at 80 degrees Celsius and maintained a tension ratio of about 50%. The fiber bundles were then made into a braided wire through a mini-type braiding machine. In this close-up image, you can see the braided nanofibers. Next, for our antimicrobial sutures, you can see that polycaprolactone fibers were incorporated with ampicillin sodium salt. Ampicillin is an antibiotic, which would have antimicrobial properties. This was used by a thin desk electrospinning collector, and that's what they used to collect the nanofiber bundles. The fibers were then twisted into yarns using a twist tester by Alfred Suter Co., and the amount of twist was 5 twists per inch. Each yard was also made of 0.1 milliliters of polymer solution, which is interesting to note since we determine our amount by spin time instead of amount spun. In this image, you can see that as you increase the drug load, you inhibit the microbial presence of the sample. Now, there's also sutures for ocular surgery. In this, they actually used wet electrospinning to manufacture sutures composed of PLLA, PEG, and the antibiotic levofloxacin. The sutures were manufactured in wet electrospinning. They were actually found to be 45.1 plus or minus 7.7 micrometers in diameter and had a 0.099 plus or minus 0.007 newtons in breaking strength. From this, they actually decided that the tensile strength needed to be improved prior to clinical use, which is important to note since our device would solve this issue. And they also showed that the antibiotic release profile demonstrated a burst followed by a sustained release for greater than 60 days. This image shows the wet electrospinning method and what a typical suture from this method looks like. Now, as for the engineering aspects of this, the engineering requirements, this design requires multiple considerations such as mechanical strength, diameter, and tightness, as well as the accuracy and precision. For mechanical strength, There is one requirement, and that is set by the U.S. Pharmacopoeia, in that it requires a synthetic 4O suture have a 9.32 Newton knot pull tensile strength, and a collagen 4O suture have a 7.755 Newton knot pull tensile strength. In this instance, we are looking at the 4O suture because that's what we are working with, because 4O is used for vascular surgery and our current applications are to that of vascular surgery. But this chart here shows that the knot pull tensile strength for these fibers, this is for the synthetic fibers. Diameter and tightness is also a requirement that we need to consider when engineering this device. So this also shows that a 4O suture must be between 0.15 and 0.19 millimeters in diameter, and that it's important for the sutures to remain tight or have a high twist per inch ratio so that they have that optimal surface area to volume ratio for optimal drug delivery. This chart shows that suture diameter recommendation for each size suture. And then finally, they also need to be accurate and precise. This is important for reproducibility, documentation, and industrial use. And basically, we need to have these fibers be accurate and precise in their diameter, their tensile strength, their adhesion to the suture, their shelf life, and their twist per inch. Where we can improve, this will go over our current methods for optimization, and then how we could potentially improve consistency and adhesion in the future. For our current methods, we are experimenting with rotational speed, brush head size, and the distance between the frame in order to optimize that uniformity in the twist of the suture, the alignment of fibers, and the coated suture diameter. So currently we do need to improve that consistency because the fibers aren't currently consistent throughout the suture. The middle is very loose, whereas the ends are tight. So we will attempt to fix this by manipulating the brush head size, rotational speed, and the distance of the frame collector. And then it's also important to note that we could improve the consistency of the individual fibers themselves just by having a better mechanism to control humidity. In this first image, you'll see the middle of the coated commercial suture where the fibers are very linear and they're not twisted, whereas compared to the ends where they are extremely twisted and not nearly as linear as the middle. There's also a need to improve the adhesion so that the suture can actually act as a suture and that the electrospun nanofibers will not dislodge from the commercial suture in surgery. And so this will just see how the fibers will hold up under tensile test. And it is some ideas to improve this adhesion or attachment could even be to rough up the suture surface to catch the fibers better, or to coat the commercial suture in order to adhere the nanofibers to the surface. And lastly, these are the sources, and that is it. Thank you.